We are very happy to have Arjun Ramachandra with us today. Arjun did his integrated undergrad and masters from IIT Kharagpur. Then he went to do a PhD in operation research at National University of Singapore, the Singapore University of Technology and Design. At Singapore University of Technology and Design, he also did a postdoc. His research interests lie broadly under optimization and uncertainty, and today he'll tell us about the interplay of submodularity and uncertainty. Looking forward to the talk. What do you?
45 minutes? Whenever you want it. Good morning. Am I audible? Okay, great. So thanks, Mohit. It's my pleasure to be here. Thanks for the warm welcome. Being at IISc actually gives me fond memories, brings back fond memories because almost 2 decades ago, I was here as a KVPY scholar before I went to IIT Kharagpur. So, it's been a long time, but it feels like coming back home. So I want to thank all of you for being here today, sparing your time to listen to this talk. So I'm going to talk about an ongoing research project, which I've titled it as Interplay of Submodularity and Uncertainty. So this is joint work with Karthik Natarajan, who is my one of my advisors, PhD advisors, and who is currently a professor at the Singapore University of Technology and Design. So let me straight away, just get into some introduction of submodularity. I'm sure many of you will be familiar with, the notion of submodularity, but just to set the scene. Before I do that, I just want to say, please feel free to interrupt me in case you have any questions or clarifications or comments as we move along. Typically, when you talk about submodular optimization problems, so you consider a ground set of n elements, and you have basically this, what we call 2 raised to n, that's the power set basically of this ground set. And you consider a non-negative set function, which is a discrete set function. It's a discrete function where the input is one of these sets and the output is a non-negative real number. And now this particular set function, for the sake of our talk today, will be assumed to be submodular and non-decreasing. So what is submodular, we will come to soon. But essentially, the point I want to make here is that we are looking at this discrete functional property. And this non-negativity again is without loss of generality. When you have, negative function values, you can actually deal with them and you can basically reduce them to this setting. So that's why we are considering this setting. We will also be assuming a few more things about this function, which we will come to later. But what is submodularity? Essentially, in very simple terms, so if you think of S and T as 2 of these sets, which I talked about, I mean, subsets of that original ground set, such that S is strictly contained in T, and you have an element which is outside T, basically, the larger set. So all that submodularity says is that the incremental value of adding E to S is at least the incremental value of adding that same E to T. In other words, f of S union E minus f of S, that's the incremental value of adding E to S, the smaller set, is at least, or it's lower bounded by the incremental value of adding E to the larger set, basically. So in other words, as you increase the size of the set, then adding that same element gets you less and less value, incremental value. Now, this is true for all S and T. Now, if you, apply this definition to, for example, the orange set here. So here you have now, please note, no longer S is contained in T here in this diagram. So there is some intersecting area. But now that intersecting area, the pink area, strictly lies in the orange area. So now you can think of, the setting which I just mentioned earlier, S intersection T is strictly contained in S, S minus T. And therefore, if you just apply that definition, right, adding this green area, right, which is outside both of them, to S intersection T should give you greater value than adding that same green area to the orange area, right? So that's basically, I'm being a bit hand wavy here. That it's not, I mean, there is a, you have to do this element by element, and then basically you get a telescopic kind of a sum, and you will end up with this kind of inequality. But the interesting thing is now, this guy here, right, what you see on the S intersection T union T difference S is basically nothing but f of t, right? So you'll get an inequality like this, and that ends up, that actually ends up saying that f of s plus f of t is greater than f of the union of the two sets and f of the intersection of the two sets. So this is an alternative way of looking at submodularity. Now, if you look at, if you consider, for example, you can take S and T to be, just two, the singleton sets, for example, 1 and 2, right? The singleton sets 1 and 2, then all that this is saying is f of 1 plus f of 2 is greater than or equal to f of 1 comma 2, because the intersection is a null set here, right? So in other words, we are saying that submodularity is saying that having those two elements separate, okay, is better than having them together in terms of the function value. In other words, I'm saying that looking at them individually, the function values individually and adding it up is basically better, or it's greater than the function value taking them together. So in some ways, this is, so this is basically the substitutive property, right? So for example, I mean, just to give a crude example, so like, tea and lemon, for example, right? So they would be more complementary. They wouldn't be substitutive. So that is the opposite of this. Whereas maybe coffee and lemon would be substitutive, right? So in the sense that it's better to have them separately than together. So this is one way in which you can think of submodularity. And also we assume monotonicity. This is important. I'll come to why we are assuming monotonicity. So essentially all that says is if you have this S and T, where S is strictly contained in T, then f of S must be upper bounded by f of T. Okay, so these two assumptions we are making on the set function. One is it's submodular. That means it's modeling the notion of diminishing returns. And second, it is monotone. It is monotonous. Okay, when I say monotonic, I mean here it's non-decreasing. Okay, that's the specific type of function we're looking at. Is this assumption clear? Are there any questions on this before I move ahead? Because this is fundamental to all our discussion henceforth. Okay. So submodular functions are all over the place. I mean, if you just read the literature, there is like I think literally an unending stream of work, partly being because submodular functions are just, they are in one sense the discrete analog of, concave functions, because as we talked about diminishing returns, there is this concavity which is playing into, which is coming into play, but there is also a convex aspect of submodular optimization, which we will come to. So it's kind of, it's in some ways concave, in some ways convex, and that's one of the reasons why it's finding a lot of applications, and also it's very intriguing, to look at how submodular functions behave. Okay, and that's the reason why I've titled my talk as, the interplay of this submodularity and uncertainty. So, I mean, I'm not going to go into each of these, but there are plenty of applications for, I just talk about maybe influence maximization. For example, in social media, so typically, you have a seed set of users who tend to influence, the rest of the users on social media. Now, if you look at it as, rumors, then yes, you want to basically, you don't want that seed set to be very influential. But if you look at it as something positive, then you want to you have something called the influence maximization. That means, you want this seed set to be intelligently chosen so that they can maximize their influence. In other words, they can maximize the spread of information through the network. But now the users can influence, each other randomly, etc. So that randomness comes into play. But my point here is, given a seed set S of, initial influential users, the reachability of those users. When I say reachability, I mean the number of people they can reach. But talking from a purely deterministic point of view, that is a submodular function, right? Because more the number of, if I have more number of seed set users, then adding another guy into that, the number of basically the number of people reachable will not significantly increase by adding a new guy there. So this is kind of a submodular flavor, which you can see here. Similarly, in auction theory and across power networks, healthcare, there are a lot of applications of submodularity. But what does the literature do? So when you have this submodular flavor, right? So essentially, what the literature is trying to look at is actually deterministic submodular optimization. So I have this submodular function, but my sets now, the sets over which I'm optimizing, they are constrained, right? I mean, if you're looking at unconstrained submodular optimization, for example, if this I here is the power set, it's a trivial problem, but because I'm assuming, it's a non-decreasing monotone. I mean, it's a non-decreasing submodular function, so there's nothing to do there. But then when you constrain it, that's when it becomes interesting. And that's also actually quite realistic, as I will show you soon. For example, here, this water contaminant network detection system. So the goal is I have some, sensors. I have some locations where I can place water contamination detecting sensors. The question is, where do I place them, right? Because I have a limitation on the number of sensors which I can place. So here, if you look at it, in terms of the the deterministic submodular optimization, I want to maximize the coverage area of each, of basically the sensors which I've chosen, right? So coverage area, meaning the union of the areas which they can actually detect the contaminants. This is a submodular function, right? If you look at this coverage function, it's a submodular function, because when you add a new sensor to, let's say, 3 sensors versus adding it to, 4 sensors, it's going to have less value for the 4 sensors in terms of the coverage area. Now, the point is, I need, let's say I have 100 sensors, which 100 locations where I have to place 10 sensors, right? Now, that's a very, very hard problem to solve because, I mean, if you want to do it enumeratively, you have 100 choose 10 possibilities, basically, right? So that's not obviously, tractable, and that's where, submodular maximization comes into play. So I want to look at, I want to find a way by which I can at least get an approximation for maximizing this coverage area, which is basically a submodular function, right? So I hope this helps you get an understanding of what the literature is trying to do. It's not easy, but they do have a lot of work on getting approximations here. Okay, but again, like I want to clarify that in our work, it's kind of, there is a very different approach which we take, which is that now I start looking at the behavior of submodular functions with uncertain inputs instead of just, assuming that, for example, in the previous example, assuming that the sensors will always function, right? Now I begin to assume that the sensors may or may not function, which is quite realistic. Depending on the locations, there might be some probabilities with which they function. So now this guy here starts becoming, this S here itself is it's a random set, because now the probability that, that particular set of sensors which I chose will work will be governed by some correlations, right? So there's a joint distribution over all these sensors. So this is no longer, it's not chosen deterministically. So this is the setting in which we are operating. So that's each element I has a probability xi of being included. So in the sensor example, each sensor has a certain probability of, functioning based on the location at which it is installed. And therefore, and there is also possible higher order marginal information. We don't know about it. We're just assuming nothing except the marginal information. So what? Yeah.
Effectively, seeing that xi is not necessarily independent.
Exactly.
Otherwise, it would be a multilinear relation.
Exactly. Yes. Yes. Perfect. Thanks for that. Yeah. So if xi's were, if the problem, if the event, okay, what's the event here? The event is basically whether the sensor is chosen or not, whether it functions or not. Now, yes, it's not, we're not assuming independence. If it did assume independence, it would become the multilinear extension. We'll come to that. But yes, in fact, the multilinear extension is one of the distributions here, if you look at it, because it's freezing the joint distribution, right? But we are interested in not just the multilinear extension or, assuming independence. We want to look at all possible joint distributions given only the marginal probabilities. I don't know anything else. So we are interested in solving problems of this type, where now you can see there's an S tilde here to indicate that the set is itself random, right? So it's no longer a deterministic setting. Now, of course, our assumptions still hold. we want to do it for monotone submodular functions, because if you have arbitrary functions, then it's going to be hard to even with monotone submodular functions, computing these expectations have already been shown to be NP hard. I will come to that slightly later.
The input you have is, of course, the submodular functions and the marginals.
Exactly.
What?
And the n, which means the size of the input, basically the number of.
Yeah, the capital, the cardinality.
Exactly. Yes.
What is the decision variable?
Exactly. So the decision variable is basically the thetas here. These are basically the probabilities which you would assign to each realized scenario. For example, if let's say sensors 1, 2, and 3 were chosen, that's going to happen with a certain joint probability. That is the decision variable. So because you see, I'm optimizing over all possible joint distributions. Or you could think of this as a convex combination of the function values at each one of these 2 raised to n possible subsets, right? So if you take the function values at each of these subsets, you're taking basically a convex combination of this. Each convex combination defines a joint distribution.
You want your search space is a joint distribution such that its marginal
Exactly.
respects xi, and the function expected value of the submodular function is as value.
Exactly. So my search space is a set of all joint distributions, and whichever joint distribution maximizes it is my optimal distribution. Exactly. So I don't know anything other than the marginals. We will come to more constraints later on. In fact, the crux of my work is when I'm going to introduce more constraints than just the marginals, and that's the pairwise independence constraints. I will talk about that as we move on. But why do we want to understand? Why do we want to study these functions? Yeah. Sorry. S tilde is basically the random set. So here the randomness is in that particular set being chosen. For example, in the sensor example, for example, sensors 1, 2, and 3 are chosen with a certain joint probability. I don't know what is that probability because I'm optimizing over all possible probabilities, joint distributions. So that S tilde is not deterministically chosen. There is a certain probability of that being chosen. That's why it's a random set. Does it make sense? Okay. So there is an interplay of submodularity and uncertainty happening very interestingly, because please note, submodularity is it's a functional property, right? And then we also have this uncertainty which is coming into play. Submodularity by definition is, when you're maximizing, what does submodularity do? Essentially, it encourages negative dependence because, as I said, F1 plus F2 is at least F12. So what it's trying to do is, it's now trying to prioritize F1 plus F2 over F12. So it's trying to keep the 2 random variables, that singleton sets, let's say 1 and 2, separate rather than take them together in the joint distribution because you want to maximize. So,
build upon other examples that show that the product distribution is very far from the optimum.
Oh, I think that's exactly what we're coming to. In fact, the product distribution and this guy here, they're not too far off. That's a famous result of Shipra. In fact, we'll come to that. Thanks for that, actually. So yeah, right. So this may be hard to compute, but it may not be hard to approximate. That's the crux of my talk today. Actually, it's good that you asked this. So it may be hard to compute this, but it may not be hard to approximate this, which is why we are going in this direction. Anyway, the point is, submodularity is encouraging negative dependence. Okay, so if your uncertainty is designed in such a way that it's moving towards positive dependence, okay, then there's a kind of a interplay which becomes interesting. If your uncertainty is also designed in such a way that you're encouraging negative correlations, then it becomes uninteresting because both are going in the same direction. But anyway, the point is, there are in the CS literature, people have looked at this kind of a problem more from an exogenous perspective, meaning that they're looking at this as some kind of continuous extensions to the discrete, to the discrete submodular optimization. But for us, uncertainty is endogenous, it's not exogenous. We are actually having, as I said, sensors having a certain probability of failing or not. But at the end of the day, whether it's exogenous or endogenous, I think the results from one stream to the other stream do, just flow over. So why is it useful? Especially why are we doing this? Because for distributionally robust type of problems, we'll come to what it means, DRO or distributionally robust optimization type of problems. This is very helpful to get a hold on this, even approximately. And then we can also get tight linear or semi-definite program relaxations if certain conditions are satisfied. But note one thing, that this F will hugely determine the computability of the optimal value, right? So the nature of F, even if F is monotone submodular, there are certain class of monotone submodular functions for which this will be easy. But there are certain class of monotone submodular functions, or rather for most of it, it's not easy. Okay. Yeah.
It built from ground up.
Yeah.
If F was not only submodular but even additive, then this would be a mood because every distribution will give you the.
Yes. You're right. Yes. If F was not just submodular, but if it was also additive, yeah.
Linearity. Yeah.
Correct.
So
Yes.
every joint distribution will excise as the marginal, the expected value.
You mean giving you the optimal in terms of?
Yeah, you can pick any, and in particular, you can pick the product distribution, and that will be the optimal.
Yes. Okay. Yes, you're right. Yes, because then you don't have the because so basically what you're saying is modularity. Modularity. Yes, you're right. Yes. Okay. So now this is the setting which the literature considers, where I here is basically what is known as an independent set. So in the predominantly in the CS literature, what has been considered as constrained submodal optimization is when you have basically these sets living in the independent sets of a matroid. What is a matroid? A matroid is basically a set system n comma I, where n is the ground set as we discussed. I is basically it's a set of subsets of the ground set which satisfy two properties. What are the two properties? First is known as the downward closure property. That means if B belongs to I and A is a subset of B, A also belongs to the independent set. So if I have an independence, if I have a set belonging to I, every subset of that must also belong to I. It's downward closed. The other property is basically if I have two sets of different cardinalities, okay, A and B, where cardinality of A is less than B strictly, then there is always an element in B which can be added to A, and still that new set A plus E would lie in the independent set. So now, okay, this is a bit abstract, but it's nothing but a combinatorial abstraction of linear independence among vectors. So you're kind of taking the concept of linear independence, extending it to sets. So that's basically what we are doing here. So for example, with linear independence, right? So when you have a set of linearly independent vectors, then any subset of them would also be linearly independent. And then the second one is basically also like we have two different subsets of of linearly independent vectors. One is larger than the other, then you can always find one in the larger set which you can add to the smaller set and still preserve linear independence. Right. So in some sense, this is basically an abstraction, a combinatorial abstraction of the notion of linear independence. And a simple example of this would be the uniform matroid. What's the uniform matroid? It's basically just all sets of cardinality at most k. It's easy to see that this is satisfying both the downward close property and the second property, right? Because if I have any set which is contained in S, that has to be obviously having cardinality less than k. And if there is a larger set, if I have two sets, which basically one is larger than the other, then you can always, and both of them are satisfying this, you can always add one element from the larger set to the smaller set and still satisfy this. So this is very commonly studied. In fact, the sensor example I just gave you is exactly this setting, right? Because I have a cap, I can at most fit 10 sensors. But because the function is monotone, non-decreasing, I will obviously choose 10 sensors. I'm not going to choose 9 sensors, right? But then I have 100 choose 10 possibilities. Even with excluding all the 9, 8, 7, 6 number of sensors, I have 100 choose 10. So even that is a hard problem. Another example for matroid is just, for 3 variables, you can see this is a matroid, right? Because you take any set, its subset will be in the, so this I is what is known as the independent set. So any set here, its subset is also in I. And for example, 1 and 1, 2, for example, right? You can always add 2 to 1 and get back 1, 2, which is in the independent set. So you will see that both the properties are satisfied. But if I remove this, let's say 1, 3, for example, from here, then it won't be a metroid any longer. Why? Because then, for example, 3 and 1, 2, you can't add 1 to 3 or 2 to 3 and get something in the independent set. You see? So metroid has certain properties which are helping us in the optimization, right? Now, of course, the free metroid is if you have the entire power set, then it's a free metroid. There's nothing. I mean, it's also a valid setting, but as I said, unconstrained maximization can be uninteresting unless the function is non-monotone. Now, if I just check out the the requirement of monotonicity, then yes, this free metroid also makes sense to consider, right? So even when you have structured functions like submodular functions, it's very hard to optimize over these arbitrary metroids. It's not easy. Yes. Sorry. Yes. Exactly. No. So you're saying, can you have 2, 3 here?
Yeah. Here we set 3 and set containing 1 to do not satisfy.
No. Okay. I say if you remove 1, 3, then it's not a metroid, right? But okay. Oh, okay. I get your point. Okay. So no. Okay. The second condition is there exists an element, not for all. You see? So for example, as you said, like, so if you consider like 3 and 1, 2, 1, 3 is there here, 2, 3 need not be there because there has to be just one element in that bigger set. Okay. So that's, yeah.
Further reformulated by saying all maximal sets are the same constant.
Perfect. Thanks for that. Exactly. Basically, the second condition which I talked about is exactly what it's saying is all maximal sets, have the same cardinality, right? Okay, great. So now, so you have similar notions like, how you talk about dimension, with vectors, right? You have basis of a vector space. Here also you have basis of matrix, metroids. You also have, the dimension of the basis, which is basically known as the rank of the metroid. Okay, so rank is basically the maximal independent set in the metroid. The cardinality of the maximal independent set is the rank, and the basis is basically all the maximal independent sets, which, as he said, are of the same cardinality. Okay, great. Now the point is that is hard to solve, the deterministic problem, right? We discussed why it's hard. So can we make approximations? The idea is to use continuous extensions. So imagine I have 2 variables. These are your, this is the power set, right? You can either have the null set, you can have 1, 2, or you can have 1, 2. Okay. Now your function values are defined on these 4 points for 2 variables. Now what I do is I now build a hypercube, or in this case, I just build this square here, and then I now consider a point which lies inside this and define an extension over this hypercube, basically. So this is called a continuous extension. Why? Because it is easier when you have, when you're optimizing over this, polytope rather than having this discrete setting. So there are results which say that, optimizing, linear functions over this kind of what are known as polymetroids. Polymetroids means the polytope, which is the convex hull of these, the function points, the indicator. If you consider the function points, the indicator function to take the convex hull, you basically get the polymetroid. It's easy to optimize over that, and that's what all these continuous extensions are doing. But yeah, the definition wise, it's just now instead of having, if you see the difference, there's an interval here instead of just, 0, 1, n, where you had the curly braces. Now you have these square brackets, which basically indicate that now it's an interval. It's a continuous, framework we are in now. So, for example, if these are the function values in red here, right? So if my f of 2 and f of 1 are 1 and 1, and f of null set and f of 1, 2 are 0, then you can build all types of continuous extensions. Now, what if you look at the convex hull of this, right? So basically, you take these 4 points in red, you build a convex hull out of it. Then essentially you can have many extensions within that convex hull. So I'll just show you a few here. This is the lower convex hull, basically. It's the what's known as the Loa's extension or the convex closure. Okay. So this, as you can see, is exactly the lower convex hull when you build the convex hull on this. So this is the least you can get, in terms of being within the convex hull. Okay. So this is the lower bound. Similarly, you can also have something in between like this. This is the multilinear extension which Siddharth was talking about. This is somewhere in between. And then you have this concave guy, the green guy on the top, which becomes the upper convex hull. So together, this green and the pink, are basically forming the convex hull of the function points, basically. So you see now, I can, so for any given, x in that square, you can compute, you can at least define these values, right? You can define these upper convex hull, you can define the lower convex hull, you can define something in between. Now, that's not enough. Okay, we will come to why that is needed. But I just want to talk about this upper convex hull first. That's known as the concave closure. All that we are doing is we are saying, in fact, this is exactly what we talked about already. I'm just considering all possible joint distributions satisfying the marginals. And of course, it should be a valid probability distribution. In other words, it's a convex combination. And essentially, I'm going to get the concave closure, which is the upper convex hull, right? Can you see why this is every, for any given value theta, this summation is basically giving you the expected value of f of s. It's a convex combination of the function points, which are the, basically the corners of the convex hull. So it has to lie inside the convex hull, right? But now you're maximizing it, so it goes to the roof of the convex hull, which is what we call the concave closure. Similarly, the convex closure is basically the minimum, nothing changed except the max to the min. Now, as Siddharth was saying, there's something called multilinear extension, where now I assume that you are basically having independent events, right? So this is how it works, right? So if you have the same setting, then the multilinear extension would look something like this, because what you're doing is you're just taking a point in the middle of this, you're rounding it off to the corners independently. Okay, so you take a point in the hypercube, round it off independently to the corner points. That's what we're doing here, right? If you look at this, all that is saying is for every s, I take the product of the probabilities for those elements which are in the set and 1 minus the probabilities for those elements outside the set. That's exactly the independent distribution. So now all these extensions are there, but what are we going to do with this? That's the question, right? So, okay. The earlier example I showed you was a non-monotone example, right? You can see here, this wasn't monotone because F12 was 0, F1 was 1. That's not our setting, so we need a monotone example. So this is a monotone example, right? You can see now that 0, 1, 1, 1 is a monotone submodular function. This is how the lower convex hull looks like. This is how the multilinear extension looks like. And this is how the green guy here is the concave closure. As you can see, the names are pretty appropriate. Concave closure is concave, convex closure is convex, and multilinear is neither concave nor convex. Now, okay, one very important property of these continuous extension is that at the corners of the hypercube, they will coincide with the original function values, right? I think you must have noticed it already here. Like for example, here and here and here, you can see it's exactly 1, right? This continuous extension is also 1 at the corners, and similarly here it's 0. This is a very important property for us. We will come to why that is important, but this is how continuous extensions are defined. A valid continuous extension must satisfy this property and monotonicity as well. Now you're looking at monotonicity not in the discrete setting but in the continuous setting, right? For all y greater than or equal to x, where y and x are 2 vectors, element wise, when y is greater than x, essentially you should have f of y greater than f of x. I mean, at least f of x. Now the point is submodular minimization. Again, this is one thing which gets me excited about submodularity, is that it behaves in nature. It behaves like a concave function because of the diminishing returns property, but it's easy to minimize. Which again, that's like a kind of a convex property. So why is it easy to minimize? This is something which is intriguing, but it's not too hard to see. Basically, this guy here, the convex closure, which is what is your the lower convex hull, it's easy to find this, evaluate this because of something known as the Loa's extension. So Loa's extension basically is an extension which basically does not need a support more than polynomial number of support points. If you remember, our joint distributions are all supported on 2 raised to n points, right? But this doesn't need that. So this is basically what we call the perfectly positively correlated distribution, where every pair of elements are perfectly positively correlated. So that's the Loa's extension. It so happens that when you have a minimization of the expected value which we have, it so happens that the two coincide. This will not happen for maximization because the inequality will go the other way. So when you write the primal and the dual, you will see that these are equal. But again, the caveat is you need F to be submodular. Otherwise, it won't do. Okay, so under submodularity, these two are equal, not monotonicity. Monotonicity is not required for this. But now that immediately tells you that so Lowa's extension then becomes convex because convex closure is convex. So when F is submodular, Lowa's extension becomes convex. And therefore, now you can minimize the Lowa's extension, which has two advantages. It's convex and it is just having a polynomial number of description points, basically. It's not described on the whole support set. Now you can use the ellipsoid algorithm, for example, and solve. You can minimize this Lowa's extension of the convex closure over the hypercube. But this will not happen with the concave closure. Why? Because there we don't have the privilege or the luxury of having a polynomial support set kind of an extension like this. There it will be, in fact, it's NP hard. It's the other way around. So this again, like this reminds us of a class of problems where minimization is easy, maximization is hard, right? So again, you come across all kinds of, like for example, max cut is hard, right? So you can see that it will have its difficulty in although there is this famous result of Gomez-Williamson, but max cut is actually an example of our type of problem because of course it's not monotone, but it is submodular. The cut function is submodular. And basically, if you try to get a maximum cut, you're basically maximizing a non-monotone submodular function, and that's hard. But yeah, there is still a 0.87 approximation there, which turns out to be from this result of Gomez-Williamson. So submodular maximization is hard. Yes, sorry.
How do you know that the lower definition won't introduce any unwanted solutions? It's even part of the concept itself.
Okay, good point. Good point. So okay, see. Typically here, the Lowa's extension will have its, for example, here, this entire, this line over here, that's going to be the minimizer set of optimal solutions. So if you get a corner point, well and good, you're done. You go back to your disk, you don't have to round off or anything like that. If you don't get a corner point, suppose your algorithm outputs something in between, you can always do this rounding techniques by which you will be able to find a discrete point in the vicinity of this corner point, so that you will be able to that will also be the same give you the same optimal solution. So basically, it has that property. And the main reason why it works is because you just have to deal with a few support points. You don't have to deal with all those exponential number of support points. Now, by the way, if you talk about the concave closure, even that would have its maximum at, if you look at it, because it's anyway the upper convex hull, it would also have its maximum at one of those corner points. So one might think, well, then can't I just solve it and get, go back to my discrete setting? The issue is computing the concave closure is not easy, unlike the convex closure. So you see, to optimize, you need to first compute, then you can optimize. So in the case of Lowa's, the convex closure, it is easy to optimize. It's easy to compute. And therefore it's, and then subsequently, it's also easy to optimize, right? So that's the setting we are in. So anyway, but submodular maximization, there are all kinds of approximations. I'm not going into too many details, but there's this 1 minus 1 by approximation for uniform matroids and also for general matroids. Now the interesting thing is this is actually this is tight. You can't do better than this. Okay, in general you can't do. You can do better for specific submodular functions. And the assumptions are basically you have monotone submodularity, you have oracle access, two types of oracle access. I should be able to query the function value for any arbitrary set, and I should be able to query whether or not a set is independent. Okay, if I can do these two oracle queries, then I'll be able to get these approximations. Okay, and by the way, these approximations heavily depend on monotonicity as well as submodularity. You wouldn't be getting these if they were, for example, non-monotonous. In fact, for non-monotonous submodular maximization, you have a 0.5 approximation. Okay, so that's basically so again, like unconstrained non-monotonous submodular maximization. There's a 0.5 approximation. In fact, I think Mohit has this very interesting work on a half plus epsilon deterministic approximation for submodular maximization problems. So typically, 1 minus 1 by E you get with this kind of randomized approximations. But his work is doing a deterministic in a deterministic setting. What was known was a half approximation, but I think they've managed to get a half plus epsilon approximation. So yeah, so basically these are some of the assumptions which are needed. But let me just quickly take you through why it's helpful to have this property of, as I said, the continuous extensions basically are identical with the function values at the corner points of the the convex hull basically. The reason is because then when you maximize these extensions, f tilde as an extension, when you maximize these extensions over that convex hull, the convex hull I'm just representing with the P of m is a polymatroid. It has to be lower bounded by the what we want. This is what we want, right? Max f of s belongs to the independent sets. So it has to be lower, this has to be an upper bound simply because you're counting all those points plus more within the matroid polytope. So this has to be an upper bound. Now, once I have this, what I can do is I can now try to either evaluate this perfectly or get an approximation on this guy on the left, right? And then what I do, I should be able to round it off effectively to get back a discrete solution. That's the crux of all the literature, mostly, not all, but most of the literature on submodularity. So you get this alpha approximation on this guy. For example, here, this is the multilinear extension. So multilinear extension can be computed. Actually, you need to sample. This also, it depends, this is randomly sampled over here, which is why all these algorithms are, random. So this, you get an approximation, you get this x star, which is the max of this guy, and you can then just jump on to the multilinear extension and then round it off. Now you might ask, why are we jumping on? Like, for example, imagine I'm going on this green, the concave closure. I can basically, get to the optimum solution, but the problem is rounding off, because in rounding, you shouldn't lose the approximation. So the interesting thing about the multilinear extension is, although it's neither concave nor convex, it is convex in certain directions, which are very useful. So I can jump from this green guy, wherever I reach optimality, I jump to the yellow guy here, which is the multilinear extension. And I basically round off from the multilinear extension without losing the approximation guarantee. So that's the whole idea, basically. Because the multilinear extension is convex in certain directions, whereas this is concave, the green guy here, the concave closure is concave, I need convexity to ensure that I don't lose anything by rounding, which is why I jump onto the, basically to the multilinear extension. So I'm able to, ensure that rounding doesn't cost me anything. And therefore, then basically I have an S star, which basically will give me an alpha approximation for the original problem, which is where all these results are showing up, which I just showed you, 1 minus 1 by E. Alpha is 1 minus 1 by E in the earlier settings. Okay, now, what we want is, just to compute the concave closure, right? We are not maximizing the concave closure over the matroid polytope. That's not our setting. Our setting is just to compute the concave closure. Can we do it or not? As I described, it's not easy. It's an NP hard problem, but can we instead just say that, for example, here, these two guys are not too far away. Maybe I can't compute them precisely, but can I say it's not too far away? And interestingly, yes, we can say that. In fact, that's the famous result of Shipra. Between these two, the gap cannot be more than E by E minus 1. That's the result which, we will talk about as well. Okay. So the idea is, as I said, let's just ignore the correlations, which you will get in the concave closure. Let's just consider the multilinear extension. Because multilinear extension, at least you can sample and you can at least get an approximation for the you can estimate the multilinear extension. But you can't do anything about the concave closure because, there's a whole set of joint distributions there, which you really don't know what to do about. So the idea is, can I ignore the correlations in the concave closure? Can I just use the multilinear extension and approximate the concave closure? You see, that's the whole idea. So this is where the notion of correlation gap comes into play. Very simple. F plus by F. I hope I don't bother you with too much, symbols and notations here, but basically F plus, if you can remember, it's a concave closure. Capital F is the multilinear extension. So I just want to know whether this ratio is, upper bounded by some finite value. That's all. That's the hope. Because, sorry?
For all
Exactly, for all x. Right? So interestingly, this is the result. It is true that this ratio cannot be more than E by E minus 1. What does this say? This says that with submodular functions, there is something happening there. There is some interplay between the submodularity and the uncertainty, which is ensuring that this ratio is not too large. By the way, if I make the function supermodular, this ratio can be arbitrarily large. That's so therefore, there in that setting, we don't get these kind of interesting results. So submodularity is somehow playing into the picture here, and it's getting you this type of useful bounds, right? So you see the value is that I can't compute maybe this numerator, but I can estimate the denominator, and therefore I can get an approximation, a 1 minus 1 by approximation on the numerator. Now, yeah, so even with two variables, you can clearly show that either if submodularity breaks down or monotonicity breaks down, that means you assume non-monotonous submodular functions or you assume monotonous supermodular functions. In both cases, you're going to have arbitrarily large correlation gap. So I hope this word correlation gap is clear, because Chipra, who introduced this term, basically wanted to say that I ignore the correlations. So then what's the gap between having a correlated model and having an independent model? So she calls it the correlation gap. So now if you go back to that example which I just showed you, right, the deterministic submodular approximation, the getting that 1 minus 1 by approximation, that's exactly this blue, what I've highlighted in blue here is exactly the correlation gap, right? Because f plus by f is exactly the correlation gap. So in the process of proving approximation guarantees for deterministic submodular problems, you end up getting, basically guarantees for the continuous extensions. It's kind of an in-between step. So that's one use of correlation gap. The other use is in the distribution DRO setting, basically. So if I, don't just consider these expectations inside, but I have a, decision to make. Okay, so this is like a, kind of a two-stage framework where you have this X, and then, basically there is the uncertainty. Even this kind of a DRO setting, okay, you can actually upper bound by the correlation gap. So if I can prove upper bounds on the correlation gap, I also proved upper bounds on the DRO problems, basically. When I say DRO, I mean the distributionally robust problem. Typical DRO problems are having this kind of a two-stage framework. Okay, now there are 3 degrees of freedom in our problem, right? Our problem is pretty simple, maximizing expected value of a submodular monotone function, subject to all joint distributions. But there are things which can change. Number 1, the random input size. Number 2, the submodular function f, right? You can have in the class of monotone submodular functions, you can have many functions. And then number 3, the probability vector x. So now our question was, can we relax the independence assumptions? Okay, instead of assuming total independence, mutual independence, can we assume a weaker form of independence and get better approximation guarantees? Right? Because independence is a very strong, although it's easy to estimate the multilinear extension, it's still a strong assumption. So we said, okay, let's take some other assumptions, and can we then say something like this? For all, if I have these 3 degrees of freedom in full generality, any n, any function, any marginal probability vector, can I get better approximations? That's the first question. If I can't do it in full generality, can I restrict one of the degrees of freedom and still do it? Right? For example, I take small n, maybe I take small probability vectors and keep the other 2 general. You see the point? So can we at least do the second one if we can't do the first one? Now, I just want to talk a little bit about, pairwise independence as a concept. So I'm sure all of you are familiar with this, but pairwise independence is a weaker notion of complete independence, right? Because mutual independence implies pairwise independence, right? But pairwise independence does not imply mutual independence, because there could be higher order dependence. 2 variables could be pairwise independent, but 3 of them could be dependent. But that will not happen with mutual independence, because if, let's say, 10 variables are mutually independent, then every 9 of them, every 8 of them, every 7 of them have to be independent, which means every 2 of them also have to be independent. So therefore, mutual independence implies pairwise independence. So what we are assuming is a weaker notion of independence, and it's not actually unrealistic. For example, there's a very interesting paper by Sneedman and his co-authors, where they show that in the cortical area of our brain, there are these neurons which fire. But it so turns out that these between pairs of neurons, there is almost 0 correlations, very weak correlations. But then there are higher order dependencies. What I mean to say is, when they fire together, There are higher order dependencies, but in pairs they are almost uncorrelated. So here's their graph over here. You can see the histogram of the correlation coefficient very close to 0, and the observed probability of having, let's say, 15 cells spiking in this window, 15 neurons, it actually follows the red curve. You can see the probability is greater than the blue curve because the blue curve is assuming independence. The red curve is assuming pairwise independence. There's higher order dependence basically. So the probability will naturally be, greater. So this inspired us to, kind of investigate what happens. Mathematically also pairwise independence is very interesting because it allows for smaller subsets, support sets basically, right? So you can see here, if you put a mass of 1/4 on these 4 points, it is sufficient to define a pairwise independent distribution. Similarly, the other 4 points, you can put a mass of 1/4. This is with n equal to 3. Whereas with mutual independence, you will need to put a mass of 1/8 on all the support points. This is assuming that each random variable has a probability of half. So you can see that the small support, this pairwise independence supports, or rather, it allows for small support sets, which is a big advantage, especially in de-randomization, right? Because you don't have to go through all those sets. But of course, the challenge is to evaluate, because now you have more constraints, right? I mean, you have like all these pairwise and n choose 2 constraints. For every pair, you have these constraints which keep coming up. Anyway, so we said, let's go one step ahead. Let's define what we call as a pairwise independent extension. So you have the concave closure, you have the convex closure, you have the multilinear extension, and now let's call it a new one, pairwise independent extension. It's very similar to the concave closure. The only change you will observe is this constraint here.
You should say via lesser,
Via?
a lesser higher, like LP higher or convex higher.
Yeah, okay. So, okay, here, this is a formulation where you are basically having more constraints in the sense that this feasible region, okay, which is a polytope, is contained in the feasible region of the concave closure. Because here I'm having an extra set of constraints, basically.
This is still like it with like more constraint, but still in LP because XI and XJ.
Exactly. And basically, yeah, you're right. Xi and Xj are given. I don't need, so but for example, this could be Xij, right? Xij. So then it becomes a general bivariate problem. Okay, there even feasibility is a hard thing to guarantee. But here, feasibility is always guaranteed because the mutually independent distribution is always a valid distribution here, right? As I just said, mutually independence implies probability. But when you make this general, bivariates, if I make it just Xij, then it's going to be hard unless you can guarantee feasibility. So the point is, we have just introduced one extra constraint here, and we call this the pairwise independent extension. Where will this lie? This will lie between the upper convex hull and the lower convex hull. Will it lie above the multilinear extension or below? It has to lie above, right? Because this has less restrictions than the multilinear extension. So this is somewhere between the concave closure and the multilinear extension, basically. Now with 2 variables, there is no difference between pairwise independence and mutual independence. They're the same because they just have 2 variables. So then they would match, right? But otherwise it will not match. So our question was, we know this result from Shipra, right? Can we now instead have in the denominator F++, where F++ is our pairwise independent extension? You see the point? Instead of multilinear, can we have F++? What is the advantage? F++, right? If you look at the hierarchy, basically, f of x is less than f plus, f of x is less than f plus plus, which is less than f plus. So f plus plus is closer to f plus than f is to f plus, right? You see the point? If you look at that, if you remember the convex hull which I showed you, it will lie in between. So therefore, this is bound to give you better approximations. But the question is, maybe for some, it will be true for some x, but there will be some marginal probabilities for which you'll go back to e by e minus 1. So our question was, in the worst case, can you guarantee that this pairwise correlation gap is always upper bounded by the original correlation gap of Shipra? In the worst case, which means, it's like a universal improvement for all probability values. And it turns out,
like F plus, it would be the case that the pairwise, so F plus is also computationally hard.
it is, in fact, it is hard. because you can just show by adding this set of constraints, if you look at the dual problem, it's going to be at least as hard as F plus. It's not going to be easier.
Not a computational pursuit, rather.
Yes.
Analytic.
It's not a computational pursuit because anyway, we don't have hope for even evaluating F plus. But the idea is, if you can get better approximations than E by E minus 1, then the DRO setting also you can get better approximations. So in fact, that's what we're going to show. You can reduce the E by E minus 1 to 4 by 3 in this setting, which is a significant improvement. And this is it's a worst case improvement, not it's not just a one-off case. So okay, this is our result actually. So this is followed. It's a kind of followed from series of works which we had, but essentially this is the crux of our result. F plus by F plus plus is always upper bounded by 4 by 3 for monotone submodular functions. So now, we proved it for a few cases. First, we proved it's true for the union of elements. That means when your submodular function is basically, just 1 if it's not a null set, it's 0 if it's a null set. So then the expectation of that submodular function is the probability of the union. And in that case, we showed that this is true. Now, please note that's a specific submodular function. Now, then we said we'll reduce the dimension of the problem. We'll take only 2 variables or 3 variables, but then we'll not have any restriction on f and x. Then also we're able to prove it. And then we said, let's now restrict the probabilities and let's allow n and f to be free. So in all these 3 cases, we are able to actually prove that this is true. And then there was another case where we have this kind of submodular function. These are known as, k unit auction functions. In the auction setting, basically, if you have, this k items which you're auctioning, and if you have, n number of agents. So basically, this minimum of s comma k, where s is the number of agents whose valuations exceed your offer price, which is a random event, right? So essentially, you have only k items to give, so you can only give k if there are more agents whose values will exceed. If not, you'll be able to give whatever is the cardinality of s. So this is in the auction setting. For this type of specific submodular functions, you can further improve 4 by 3 to 4k by 4k minus. As you can see, 4k by 4k minus 1 is upper bounded by 4 by 3. So the point is, we are able to do all of this for restricted, degrees of freedom, right? We're not able to do this in full generality yet as of now. You can't, like for example, in this case, I can't do it for all f, no restriction on n and x and f if I say we are not yet able to do it. And that's partially because this computing these two guys, it gets quite hard. And at least our proof techniques, how we proved this was for small dimensions. We just proved it using, extreme points of the polytope of these submodular functions. But as you go into higher dimensions, it's going to become hard. Okay, I guess I'm running out of time now. 3 minutes. Okay, great. So let me just maybe I will just take you through, why this, it gets hard. Let me just quickly take you through this. For 2 random variables, if you are looking at f plus and f plus plus, okay, the distributions are pretty straightforward. This is the distribution when the probabilities are less than 1. When you add up the probabilities, it's less than 1 or it's greater than 1. This is the distribution. Now, this distribution, okay, does not change with f. It's function oblivious. That's the interesting thing. Similarly, this distribution here is function oblivious. So for 2 random variables, we have this advantage that the submodular function, the optimal distribution which attains f plus and f plus plus, they are not dependent on the submodular function. But the moment you go to 3 random variables, that doesn't hold true any longer, right? In fact, here's a simple example. When you have this as a submodular function, these are the values. This is your f plus and f plus plus, and you can see the distribution here, the blue points. The moment you change the submodular function, you're having, the distribution supported on some other set of points. So this is a challenge. So because of this challenge, you can see here also, like, here, for example, we are changing the 2 of these function values, and we are getting all kinds of, like this f31, f21, f32 are all basically sub-polytopes of the, submodular polytope. So that means depending on whether I'm in f31 or f32 or f33, I'm going to get different values of the concave closure and similarly different values of the convex. So we were still able to do it somehow for 3 dimensions because, there you can characterize things with a little bit of difficulty. You can still get closed form solutions for f plus and f plus plus. But again, coming back to the title of my talk, there is an interplay between the uncertainty and the submodularity. That's showing up here. I need to now divide the, hypercube, the probability hypercube into all these regions. I need to divide the submodular polytope into sub-polytopes. And then I need to look at the interaction of this guy with all these regions, this guy with all these regions. So it becomes a very complicated mesh. It will surely not scale to higher dimensions. So this is just a sample of how complicated things are, even for 3 dimensions. These are all my dual feasible solutions for each of these sub-polytopes, right? So anyway, so submodularity was used in the construction of the dual solutions. Monotonicity was used in the extreme points of the submodular polytope, and essentially we just managed to prove it for n equal to 3. But that we do have a result for general and also, but you need to compromise on the probabilities. Okay, so with this, basically, I think I will conclude my talk. So I think the take home from this talk is that when I compromise on the strong assumptions of independence, for example, as we did in the correlation gap, when I assume weaker notions of independence, you can get better approximation guarantees, right? Now, it may be hard to, the other big talk away from this talk is, even though it may be hard to compute F+, it may be possible to show how close they are to each other. And through that, you can also get bounds for DR, distributionally robust problems, which are very, again, relevant in the real setting, real world. So thank you very much for your patience. Yeah, I look forward to whatever else.
Any questions? Can you speak a few words about how the standard correlation gap is established with the Shipra?
Oh, okay. Okay, interesting. Yeah. So basically, okay. So they have this. Shipra's work was earlier proved by Kalinish and others. So they have Wondrak. So James Wondrak is in MIT, so Stanford, I guess. So the way they proved it is, basically they have this Poisson process. Okay, so they run a Poisson process. It's a kind of continuous greedy kind of flavor, and they show that you can basically in situations where you can compute that convex closure, the concave closure, for example, the F+, then you can basically take that optimal value and you can use that with this in conjunction with this Poisson process to basically get an approximation for the multilinear extension. Now, there is a follow-up paper of Wondrak also. By the way, this earlier work of Kalinish is only for the Bernoulli set. Shipra generalized it to arbitrary random variables, right? So continuous random variables. But the real landmark work was of this 2011 work of Wondrak, where they showed that even for arbitrary matroids, you can get this 1 - 1 by approximation. So there they essentially use this fact. So there they don't deal with concave closures at all. They just look at the multilinear extension. They say it's concave in certain directions, it's convex in certain directions. Exactly. So now, in the directions in which it is concave, I can hitch a ride on the multilinear extension till I reach a certain point. Once I reach that point, I will now move in the directions in which it is convex. So I round off without losing it. Similar to the idea which I described, right? So you hitch a ride on the concave closure till a certain point, till the optimality. But since rounding is a problem, you drop to the multilinear extension and then round off. So that's pretty much the idea which they're using. They're using this critical property of convexity, concavity, and monotonicity. Also, they're using. Actually, monotonicity is also very important. So that's why I said the 1 - 1 by E will not continue to hold if you had non-monotonic patterns.
Based on the set of results mentioned,
Yeah.
The gap problem for this F+ and F++ is open even for the metroid rank functions.
Exactly. No. Okay. So for the deterministic setting, okay. So we really don't have much hope to use this result in the deterministic setting, because as I said, the 1 - 1 by result which is there in deterministic is already a type bound.
No, I'm just now looking at bounds between F+ and F++.
Yes.
So I'm only looking at correlation gap without any
Okay.
sort of nefarious computational
Okay.
things. And the point is that this ratio,
Yes.
is it for F, like I'm now, instead of restricting N or X, I'm going to restrict F to be a rank function of a matrix.
Yes.
submodular.
Yes.
Even then this is spoken, whether it's probability.
Oh, no, so that was the result here. So then it becomes 4k by 4k minus 1, if you remember.
No, that's for the K uniform matrix.
Yes,
the
yes.
General matrix.
Oh, okay, okay. Oh, that's a good point. Good point. Yeah, okay. So if I,
Okay.
okay, great point. Yeah. So then it's still an open question. Yes. So I mean, again, maybe for linear matroid, graphic matroid, you might end up getting, maybe something between 4k by 4k minus 1, 4 by 3, to be less than that. But yeah, I mean, yeah, at least, yeah, I wouldn't, I have not come across any result no. Yeah, by the way, this 4 by 3 result, it's not just for pairwise independence, right? Imagine if you just relax that pairwise independence to positively correlated, joint distributions or negatively correlated. That actually will also, the same 4 by 3 bound will hold for those type of settings also, because that is, basically a relaxation of the pairwise independent setting, which means the f plus plus x is going to increase. The denominator is increasing, means the correlation cap can only reduce. So you are anyway in 4 by 3. But yeah, I mean, the question is whether we can come up with better bounds in 4 by 3 in the setting which Siddharth mentioned, where you can assume, some specific graphic or linear matroid kind of a thing, and or maybe like this kind of tweaking of the pairwise independence to, positively correlated, etc.
Sorry, I missed it. So where was 4 by 3 tight? Is it tight? 4 by 3 is a tight ratio.
Oh, yeah. Okay, it's tight. Yeah. Thanks for the question. Actually, I didn't. I think here probably. I think it's not. I didn't explicitly mention it here, but yes, this ratio is tight for the union bound function. Basically, when you have the union of probabilities, actually, it's not too hard to see. If you just take, two random variables, for example, the f plus x, when you have the, union bound function, is basically the probability that, x1 plus, the c1 plus c2 is at least 1. That's basically your Boole's bound. Minimum of x1 plus x2 comma 1. This denominator, we have another result, which can also be characterized in closed form. If you take their ratio, and if you assume x1 and x2 to be half, the probabilities to be half, you're going to get half plus half by half plus half minus 1 by 4. That's basically 1 by 3 by 4, which gives you 4 by 3. So the point is, this is tight. Okay. So in general, you cannot, improve this for arbitrary monotone submodular functions. This is tight. But the interesting thing is, the functions which are, making this tight are the simplest functions. If you take more arbitrary submodular functions, this ratio will be much smaller than 4 by 3. Our experiments show that. But the extremal submodular functions are the simplest type of submodular functions, which is also something which is intriguing, or rather something exciting, because that means the answer is not possibly too hard. If you can show it for simpler functions, it may be there. Yeah. Thank you.
So let's thank the speaker once again. You are welcome to join us for lunch, and Professor Siddharth Burman will hand over this token of appreciation from our side.
You can change the shirt if you take the size.
Okay.
Copy to.
Sure.
You just take the look and
Thank you so much. That's the kind of. Yeah, I'm not. I think I'll need smallest of that.
Okay, we can walk over and they have different sizes and some different colors. We stop the recording. Things are for this.
Say stop. So.
We upload it on the. He bought this. These are new KVN.
I don't know, like they were there here, like for the earlier talks also. Yeah.
I mean, they don't they're like lapel things. So not you don't have to carry things in the.
So they will come up.
I think you can click leave, so saves it and they'll take care of the rest.